Let's look at a few more examples. Your goal here is to find the derivative function. And so you're given a function, it's called r of t. If you need to organize your paper in such a way where you could define things off to the side, so that way it doesn't clutter your main paragraph, which is off to the left. So off to the side, aside for me means off to the right. So off to the right, I'm going to go ahead and write f of t plus e to the t, and then g of t is the other function. Now when we take the derivative here, I'll go ahead and highlight the product rule with the derivatives highlighted in a different color. And so hopefully that helps you see some of these derivatives. Now you got to rely on algebra and try to just simplify this a little bit, make it look nicer. We could still simplify this. Look for the greatest common factor. Looks like we want to collect like terms and then look for the greatest common factor. So why don't we do that? Why don't we collect like terms first? There's not a whole lot you could do here. There's actually no like terms. Out of these 6 terms, there aren't any like terms. So the only thing left to do is probably write this in radical notation. And we could leave that to be the derivative function. I'll write a second sentence here. We'll write it back in prime notation or function notation. And we could let the derivative look like this. Let's look at a couple examples where you need to find the derivative function for a quotient. As usual, if you need to make room on your paper, leave yourself lots of room on your paper, and if you need to organize any labels, I recommend that you put them aside and you can label them off to the far right. Now I am going to label this a little bit different. So I'm going to label this with, well, actually I am just going to label it with f of t is equal to a times t. And g of t is going to be this. Let's go ahead and implement the quotient rule. Remember, in the quotient rule, you never expand the denominator. Always just leave it as quantity squared. Let's go ahead and do this. I'm going to go ahead and use Leibniz notation. I don't want you to ever forget Leibniz notation. Very, very powerful notation. I'll highlight the derivative in a different color. And remember, never expand the denominator. Never, never expand the denominator. Always leave it as quantity squared. If you expand it, you're wasting your time. And you don't have time to waste. You have plenty of other practice problems that you could be doing. Look at this very carefully. And ready to finalize this with function notation. I'm going to go ahead and write it back into prime notation, which is a function of t. And I realize I could simplify this even more. So I'm going to go ahead and do that. Let's take that therefore off. Let's factor the numerator. Take out another greatest common factor. And then write what's left. And once again, never expand the denominator. Always leave it as quantity squared. If you expand the denominator, you're doing something drastically incorrect. So there are actually three separate sentences here. I'm going to circle all of them. There they are. There's their three periods. So 3 separate sentences there. You are working top to bottom to get that derivative function to come out of this. Let's look at one more quotient function, and let's implement the quotient rule to this. However, notice this is a complex function because it has complex fractions in a fraction. So fractions inside a fraction is often called a complex fraction. And what we want to do here is actually simplify this first by multiplying by the least common multiple of 1 and x. That means I'm going to multiply this by x over x, and we'll simplify h of x to make it a lot nicer looking. And then go ahead and perform the quotient rule. Now I'm going to go off to the side and label my f of x and g of x. Now realize in the original domain, x cannot be 0. Ready to do the quotient rule now. I'll highlight the derivative in a different color. And remember, when you put this over the denominator squared, you never expand that denominator. I'm ready to conclude this with prime notation or function notation. And there it is. There's the derivative of that quotient function.